Welcome to the Deep Dive, where we take a stack of compelling sources, unearth the most fascinating nuggets of knowledge, and leave you well-informed and ready to tackle the complexities of our world. Today, we're diving into a question that literally touches every single one of us. What does it truly mean to age? Imagine this scenario. A pair of identical twins, let's call them Eleanor and Evelyn. Both are chronologically in their 50s. They were born on the very same day, shared the same childhood, grew up in the same house. You'd expect their health journeys to be pretty similar, right?
You would think so, yeah.
But fast forward to today, and their realities couldn't be more different. Eleanor is vibrant, active, cycles every morning, enjoys robust health. Evelyn, on the other hand, struggles significantly with chronic illness, feeling tired constantly, and facing health challenges that really just don't seem to match her chronological years. There's an immediate dissonance here, isn't there?
Yeah.
Despite sharing the exact birth date, their felt reality of aging is profoundly different. This striking contrast immediately brings us to our central enigma. What is true age, beyond just the simple count of years since birth? How do we even begin to quantify something so intrinsic, yet so wildly variable between individuals?
And what's truly fascinating is exactly that distinction. Your chronological age, the number of years since your birth certificate was issued, well, that's fixed. It's an undeniable marker of time passing.
Right.
But then we have biological age, which refers to the functional or physiological age of your body. Think of it as how old your cells and tissues actually behave. And importantly, it's dynamic, not fixed. It's a much more accurate reflection of your internal state, your current health, and even your potential longevity.
You can't change your birthday.
Exactly. But your biological age, that's constantly shifting, influenced by, well, everything from your lifestyle to your genetics.
And scientists haven't just pondered this, they've actually built tools to measure it, which is incredible. What are some of these tools that have really opened up this quest to measure our true biological age?
Absolutely. The most prominent examples, and arguably the ones that have truly revolutionized this entire field, are the DNA methylation epigenetic clocks. But it's not just epigenetics. We also have a growing suite of functional tests, blood markers, and even advanced imaging techniques contributing to this picture.
Okay, so epigenetic clocks are key.
They really are. If we were to apply an epigenetic test to Eleanor and Evelyn from your example, the results would likely be stark. Eleanor, our healthier twin, might have her biological age reported as closer to 45. Her body, at a cellular and molecular level, is functioning like someone much younger than her chronological 50 years.
Wow.
But Evelyn, however, despite sharing the exact birth date, might find her biological age reported as resembling someone well into her 60s. And this isn't just a number, it's a reflection of deeper biological wear and tear,
A huge gap.
A huge gap. This profound difference powerfully illustrates that chronological age is, quite frankly, an insufficient indicator of true health status. The core insight that has emerged from years of rigorous research is unequivocal. Biological age measures can better predict an individual's health trajectory and longevity than simply relying on their birth certificate age. That's not a subtle nuance. It's a fundamental paradigm shift in how we understand and assess the aging process.
That's a powerful statement, that biological age predicts health better than our birth year. These tools sound incredibly powerful, but with any new science, there are always a few critical questions that pop up. What's the biggest challenge that comes with this ability to measure our biological age?
That's precisely the critical challenge we're facing now. The profound question isn't just about how accurately we can measure biological age, but whether these measures truly capture causative aspects of aging.
Causative, meaning do they drive aging?
Exactly. Are we measuring something that drives aging or merely a highly accurate readout of aging that's already happened? And just as importantly, how do we ensure we use these incredibly powerful insights responsibly? This isn't just about a number. It's about the deep implications for individual health, public policy, and even how we personally view our own aging.
Okay, let's unpack this. We're embarking on an expedition into this complex scientific frontier, trying to understand the intricate landscape of biological age measurement. What's our roadmap for this journey?
Our journey today will be comprehensive, taking you deep into the heart of this science. First, we'll thoroughly explore how biological age is measured, breaking down the various generations of aging clocks from their foundational principles. This will give you a clear understanding of the what and how.
Got it. The measurements first.
Then next, we'll scrutinize their predictive power. What can these clocks truly tell us about future health and lifespan? But equally important, we'll examine their pitfalls and limitations because no scientific tool is perfect, and we need to understand their boundaries.
Right, the pros and the cons.
Precisely. A critical segment will then be dedicated to the nuanced distinction between correlation and causation in aging biomarkers. This is where the profound question arises. Does changing a clock truly change aging itself? We'll examine compelling examples where clocks and functional biological age diverge, providing crucial context.
That sounds like a really important distinction.
It's central. Following that, we will delve into the rigorous standards for surrogate endpoints, referencing criteria from regulatory bodies like the FDA. This will emphasize why meticulous validation is absolutely crucial before using any clock as a proxy for real health outcomes in a clinical or therapeutic context.
So when can we trust these clocks for making real decisions?
That's the key question we'll explore. The conversation will then broaden significantly to multimodal approaches, exploring how combining molecular data, clinical observations, and functional assessments can provide a much more comprehensive picture of biological age. It's about building a robust and holistic understanding, not just relying on one thing.
Makes sense. Look at the whole picture.
Exactly. And finally, we'll inject a necessary dose of skepticism, exploring counter-evidence and the ethical dimensions of what we might call age scoring. This will equip you with the critical thinking tools needed to navigate this rapidly evolving field.
Fantastic. So by the end of this deep dive, you'll have a nuanced understanding of biological age metrics and how they can be applied or potentially misapplied in the quest to slow aging, leaving you well-equipped to critically evaluate new claims and insights in this rapidly evolving field. Let's start by truly defining what biological age is and how we can measure it. Hashtag, what is biological age and how can we measure it? So to reiterate for clarity, at its core, biological age refers to the state of your body and its functional capacity relative to typical aging. It quantifies how old your cells and tissues appear based on specific biomarkers and performance metrics, moving beyond the simple concept of years since birth. It's about function, not just time.
Precisely. And in our detailed exploration of how this is measured, we must begin with the category that has truly captured scientific and public attention: epigenetic clocks, which are based on DNA methylation.
Okay, DNA methylation. What exactly is that?
Right. So to understand these clocks, let's first clarify DNA methylation itself. Imagine your DNA as a vast instruction manual for your body. DNA methylation refers to tiny chemical marks, specifically methyl groups, that attach to certain points on this DNA. Crucially, these marks don't change the underlying genetic code. They don't alter the words in the manual.
Okay, so the genes themselves aren't changing.
Correct. Instead, they act like punctuation marks or perhaps even sticky notes that influence gene activity. They can tell a gene to be expressed more, less, or not at all, effectively changing the meaning or emphasis of the genetic instructions. Like adding a comma or an exclamation point changes how you read a sentence.
Ah, I see. Like highlighting certain instructions or dimming others.
Exactly. The mechanism behind these clocks is fascinating. Scientists collect DNA samples often from blood, but various tissues can be used and analyze the methylation patterns. They then employ powerful machine learning models, trained on vast data sets, to identify specific patterns of DNA methylation at particular sites, known as CPG sites, that correlate strongly and predictably with chronological age.
So the patterns change as we get older.
Yes, in incredibly predictable ways across our genome. As we age, these punctuation marks on our DNA change. It's as if the body writes a signature of time on its own operating instructions.
There was a key study that started this.
There was. The landmark study here was Steve Horvath's 2013 pan-tissue epigenetic clock. This groundbreaking work identified 353 specific CPG sites across the human genome. The methylation levels at these sites, when fed into Horvath's model, achieved surprising accuracy, a correlation greater than 0.90 in predicting chronological age across a wide variety of human tissues and cell types.
Wow, 0.90 is incredibly high. Across different tissues, too.
Yes, that was the remarkable part. This was monumental because it provided a quantitative, precise measure of biological age, something we hadn't truly had before. It really put epigenetic aging on the map as a first-generation estimator, alongside Hannum et al.'s contemporaneous blood-based clock, which was also published in 2013, and equally significant for its blood-specific accuracy.
So we got these DNM ages.
Exactly. The output of these clocks is often referred to as DNM age, or epigenetic age. And here's where it gets particularly relevant for health. If an individual's DNM age is consistently higher than their chronological age, it indicates what we call epigenetic age acceleration.
Meaning their biological clock is running fast.
Precisely. And this acceleration is not just a curious anomaly, it's consistently associated with a significantly higher risk of age-related diseases and, unfortunately, earlier mortality. It's a powerful prognostic signal, almost like an early warning system built right into our DNA.
That's a great analogy, the punctuation marks in a sentence. It helps visualize how these subtle changes, not in the words themselves, but in their context, can alter the entire meaning. So these clocks are reading the punctuation of our DNA. But before these sophisticated epigenetic clocks came along, what were scientists doing to try and quantify biological age? What about the more clinically familiar approaches?
Right, good question. Indeed, long before the advent of epigenetic clocks, scientists relied on a more direct, observable approach. They used batteries of standard clinical tests. Think about it. Your doctor regularly measures your blood pressure, lung function, perhaps even your walking speed in the clinic.
Standard checkup stuff.
Exactly. These, alongside cognitive assessments and a suite of blood biomarkers like glucose levels, kidney function markers, or inflammation indicators, have always given us clues about a person's physiological state relative to their age group.
So combining those gives a picture.
It does. This led to the concept of phenotypic age. This measure combines these conventional clinical chemistry values and functional tests into an estimated age. It's a holistic snapshot of your observable health.
Okay, phenotypic age.
And a crucial development in this realm was Morgan Levine's DNM phenoage in 2018. This was a critical bridge between the purely clinical and the emerging epigenetic approaches. Levine's team first built a mortality risk score using a collection of these conventional clinical markers, things we know are strong predictors of who will live longer or get sick sooner.
Okay, so they built a risk score first.
Yes. Then they trained a methylation clock, not just to predict chronological age, but specifically to predict that mortality risk score. The fundamental goal was a significant shift, to reflect biological risk, how old the body functions, rather than just simple chronological time. It's an important distinction that highlights a growing sophistication in our measurement goals.
That makes perfect sense. We're moving from just describing age to predicting risk. Now, if we look to the very cutting edge of biological age measurement, beyond just DNA methylation and clinical markers, what else are scientists exploring? What about omics clocks?
Ah, yes, the omics. This is where the field truly diversifies and starts combining massive data sets. When we talk about omics clocks, we're referring to measurements derived from various omics fields like genomics, transcriptomics, proteomics, and metabolomics. Each offers a different lens into the body's machinery.
Proteomics. That's proteins, right?
Exactly. Let's start with proteomic clocks. These clocks analyze the levels of hundreds, even thousands of proteins circulating in your blood. Proteins are the workhorses of your cells. They carry out virtually all cellular functions.
So they're closer to the action.
You could say that. Recent, very compelling work from Harvard and others has utilized over 200 plasma proteins to gauge the rate of biological aging. The predictive power here is quite remarkable. These proteomic clocks can predict the risk of developing multiple major diseases, including heart disease, lung and kidney disease, diabetes, Alzheimer's, and cancer, as well as all-cause mortality.
Wow, that's a broad range.
It is. This suggests that analyzing proteins might offer even more direct insight into cell function and overall health decline, given their direct involvement in biological processes.
Okay, and metabolomics, that's metabolism.
Pretty much. Similarly, we have metabolomic clocks. These are based on circulating metabolites, the small molecules like sugars, fats, and amino acids that are the end products of cellular processes. These metabolites shift in predictable ways with age, and metabolomic clocks aim to capture these changes, potentially reflecting different facets of aging, such as mitochondrial function or even the activity of your gut microbiome.
So different angles again.
Different angles. And the ultimate goal in this area is the development of composite multi-omics clocks. These are still under intensive development, but the vision is to combine data from all these diverse omics fields, genomics, epigenomics, proteomics, metabolomics, and perhaps even transcriptomics, to triangulate the true biological age using a comprehensive array of biological signals.
Combining all the data streams.
Right. The idea is that the sum will be greater than the parts, providing a more robust and complete picture than any single omic measure alone.
So we've got these increasingly sophisticated ways to measure aging, from the punctuation on our DNA to the proteins flowing in our blood. But is aging a uniform process across the entire body? Do all our organs age at the same rate?
That's a crucial insight, and the answer is a resounding no. Your body doesn't age like a monolithic block. Your brain might be older or younger than your heart or your kidneys, reflecting the non-uniform nature of aging. This is where organ-specific aging measures become incredibly valuable.
Like a brain age.
Exactly. One prominent example is brain age. Here, scientists use MRI-based machine learning models trained on large data sets of brain scans. These models can predict an individual's age based on subtle changes in their brain structure. For instance, if a 45-year-old's MRI scan resembles the average brain structure of a 55-year-old, it indicates what we call accelerated brain aging.
And that means higher risk?
Often, yes. It's often directly linked to a higher risk of cognitive decline and neurodegenerative diseases down the line. It's not just an interesting observation.
Okay. And there are newer versions of this?
Yes. A particularly exciting recent development is the unpack clock, which stands for Pace of Aging Calculated from Neuroimaging. This newly developed MRI clock, unlike previous brain age models, uses a single midlife brain scan not just to estimate the brain's static age, but to estimate the rate at which the brain, and indeed the body, is aging.
The rate of aging from a scan. How?
Its innovation lies in its training data. It was built using longitudinal data from the famous Dunedin cohort, a group of individuals whose health has been meticulously tracked for decades. This allows Dunedin to forecast risks of dementia, chronic disease, and even death, because it's grounded in within-person change over time, truly capturing the dynamic process of aging.
Can you visualize that for us? How does an MRI show brain age?
Sure. Think of an MRI scan as creating a highly detailed three-dimensional map of the brain's landscape. Machine learning models then analyze subtle changes in this landscape, maybe the shrinking of specific brain regions like the hippocampus, which is crucial for memory, or perhaps the thinning of nerve fiber pathways that connect different brain areas. By comparing an individual's brain map to a vast database of other brains at different ages, the model can estimate how far along that individual's brain is on its aging journey.
Fascinating. Are there others besides brain age?
Absolutely. Beyond the brain, researchers are also developing other organ clocks. We have retinal age, which can be estimated from eye scans, immune age derived from analyzing immune cell profiles, and so on. These specific measures are vital because they can pinpoint specific vulnerabilities.
Yes. So you might have okay overall age, but one organ is aging faster.
Precisely. For example, someone might have an average overall biological age based on their blood, but a remarkably high brain age could serve as an early warning signal for neurological decline, allowing for targeted preventative strategies.
Okay, let's unpack this for a moment. We've talked about how biological age is distinct from chronological age and how it predicts health better. We've explored the cutting edge of how it's measured, from DNA methylation to proteins, metabolites, and even organ-specific insights like brain age from an MRI. So what stands out to you as the most surprising way we can now glimpse our body's true functional age?
I think what's truly surprising and revolutionary is the sheer breadth of biological signals we can now leverage. It's not just about a few clinical markers anymore. We've moved from looking at gross functional outputs to delving into the molecular intricacies of our cells through epigenetics, proteomics, and metabolomics, and then zooming out again to organ-specific imaging.
It's the multiple levels.
It really is. This ability to glimpse aging at multiple interconnected levels, from the epigenetic punctuation marks on our DNA to the subtle structural changes in our brain, is truly astounding. It represents a paradigm shift from a simplistic view of aging to a multidimensional, data-driven understanding of how our bodies function and change over time.
That's a fantastic overview. So we have these powerful measurement tools, but I'm guessing not all clocks were created equal. They must serve different purposes based on how they were designed.
Yeah.
Is it a one-size-fits-all situation?
You're absolutely right to question that. It's critical to understand that the field of epigenetic aging clocks has evolved through distinct generations, each designed with a different primary objective. This is a crucial distinction for interpreting their results.
Okay, generations of clocks.
Yes. The first generation clocks are what we call chronology predictors. Their purpose was straightforward. They were trained simply to predict chronological age based on specific DNA methylation patterns. Think of them as incredibly sophisticated guessing machines for your birth date using biological data.
Just trying to guess your age.
Essentially, yes. The prime examples here are Steve Horvath's 353 CpG pan-tissue clock, published in 2013, which we just discussed, and the contemporaneous blood DNA methylation clock developed by Hannum and colleagues, also in 2013. Their performance was truly remarkable. They achieved impressive accuracy in guessing chronological age, often showing a correlation of greater than 0.90 with actual age.
Still impressive accuracy.
Very impressive. Their utility lay in being the first reliable benchmarks. While their primary target was chronological time, they very quickly revealed something profound: the concept of an age gap. If your predicted epigenetic age was significantly higher than your actual chronological age, it indicated an accelerated biological aging process.
The gap between clock age and real age.
Exactly. Studies soon showed that even these first-generation clocks had substantial predictive value for mortality and disease risk. For instance, meta-analyses consistently found that each 5-year increase in epigenetic age beyond one's actual age correlates with an 8% to 15% rise in all-cause mortality risk.
So even just guessing age had predictive power.
It did. To put it simply, imagine two individuals, both chronologically 60 years old. If one's epigenetic age is determined to be 65, while the other's is a precise 60, the individual with the accelerated epigenetic age is statistically more likely to die sooner or develop age-related illnesses. These first-generation clocks provided the first quantitative handle on biological age acceleration and revealed that aging rates vary significantly among individuals and that this variation is somewhat heritable.
Okay, so that's the first generation. What came next?
Moving forward, we encounter the second-generation clocks, which are primarily outcome predictors. These clocks represent a significant evolution because they explicitly incorporated health outcomes and mortality data into their training. Their design objective was not merely to predict your chronological age, but rather to predict who will get sick or die sooner. They are built to be prognostic.
Aiming directly at predicting health outcomes.
Precisely. A prime example is Morgan Levine's DNAM phenoage, introduced in 2018. The construction of this clock was a crucial conceptual step. It was trained not on chronological age, but on a composite phenotypic age score. This score, in turn, was meticulously built from a set of well-established clinical risk factors for mortality. So phenoage was essentially designed to capture disease.
Based on things we already knew predict risk.
Exactly. Another powerful example of a second-generation clock is Grimmage, developed by Liu et al. In 2019. Grimmage employs a very clever two-step approach. First, it uses DNA methylation data to predict the blood levels of certain proteins and also a person's smoking exposure.
Predicting proteins and smoking from DNA.
Yes, using methylation patterns. Then, these predicted values are combined in a specific algorithm to estimate an individual's time to death. Its evocative name, Grimmage, aptly implies that higher values predict grim outcomes.
Grimmage. Sounds ominous. Does it work?
The performance of Grimmage has been impressive, to say the least. In extensive testing on thousands of individuals, it demonstrated superior performance over earlier clocks in predicting both lifespan and health span. It showed a profoundly significant association with time to death. Statistically, this link was truly remarkable, effectively demonstrating a clear connection to future health and longevity.
Wow.
Furthermore, it showed powerful associations with the risks of specific diseases, such as heart disease and various cancers. It has also been linked to other age-related conditions like fatty liver and even the age at which menopause occurs.
So these second-gen clocks are really good at prognosis.
They are. These second-generation clocks, which also include Zhang's 2017 mortality score, effectively embed clinical risk factors directly into the epigenetic measure. This makes them excellent tools for prognosis. However, because they incorporate factors like smoking and disease-associated proteins into their computation, they are perhaps one step further removed from measuring pure aging. Instead, they are highly effective at capturing an individual's damage accumulation and overall risk factor profile.
Okay, that makes sense. So what's the third generation?
Now we arrive at the most innovative and cutting-edge category, the third-generation pace of aging measures. This represents a significant conceptual leap, as these clocks are designed to measure the rate of aging itself rather than merely cumulative age. This distinction is absolutely crucial, particularly when evaluating the efficacy of potential anti-aging interventions.
Measuring the speed of aging, not just the total distance traveled.
That's a great way to put it. The premier example here is the Dundon Pace clock, developed by Belsky et al. And published in 2022. Its derivation is quite special, coming from the long-term Dundon birth cohort. a unique group of individuals whose health has been meticulously tracked for decades, allowing for within-person changes to be observed.
Right, that famous study from New Zealand.
That's the one. The mechanism of Duden pace is fundamentally different. Instead of predicting a person's chronological age or even their likelihood of death, Duden pace was specifically trained to match each person's pace of aging. This pace of aging is a separate, independently calculated metric derived from observing the actual decline in multiple organ systems within the individuals of the Duden cohort, repeatedly measured over a remarkable 20-year period. It literally asks, how many biological years is this person aging per chronological year?
So it gives you a rate, like miles per hour for aging.
Exactly. The output of Duden pace is a single value, where 1.0 represents the average aging rate per chronological year. A value greater than 1 means faster biological aging. The individual is aging more than 1 biological year for every chronological year. Conversely, a value less than 1 indicates slower aging. This provides a clear, interpretable rate.
And is it reliable?
Yes. Duden pace also boasts significant improvements in reliability. It was built using only highly reproducible methylation sites, actively filtering out noisy probes, which resulted in very high retest reliability. Its predictive power for health outcomes such as physical decline, the onset of various diseases, and mortality is as strong as, if not stronger than, grimmage. Importantly, it offers incremental predictive power, meaning it adds unique prognostic information even when used alongside grimmage for certain outcomes.
Incremental power, meaning it tells you something grimmage doesn't.
For certain outcomes, yes. And one of its most powerful capabilities is its ability to link to signs of faster aging in young adults, even decades before chronic diseases typically appear. For example, a higher Duden pace score in young adults has been associated with worse cognitive and physical function and signs of brain aging. This provides compelling support for the idea that measurable differences in aging speed are present much earlier in adult life than previously thought.
Detecting aging speed differences early on.
Precisely. And crucially, third-generation clocks like Duden pace are ideal for testing geroprotective therapies. These are treatments designed to slow or reverse the fundamental processes of aging. This type of clock allows researchers to see if a treatment literally slows the clock, reducing the pace of aging within a feasible trial period, rather than having to wait for decades of lifespan data to accrue, which is often impractical for clinical trials. Other rate-based measures include the original Duden POEM 2019 and ongoing efforts to measure instantaneous aging rates from blood chemistry.
So if I'm understanding this evolution, it's about shifting from just identifying an age to actually measuring the rate of aging, which changes everything for intervention, right?
Yes, that's it, precisely. If we connect this to the bigger picture, what's fascinating here is how the scientific approach to aging clocks has evolved. We've moved from simply predicting how old you are to predicting your future health, and even the very speed at which your body is aging. This progression highlights a growing sophistication in our understanding.
So practically speaking,
in practical terms, it comes down to your specific question. If you want to know your biological age in years, a first or second generation clock will provide that. The second generation clocks, like PhenoAge or Grimmage, will also give you a better sense of your health risk. However, if your goal is to understand how an intervention affects your rate of aging, then a third generation pace clock, like Duden pace, becomes invaluable because it's designed to be sensitive to changes in that velocity.
Use the right tool for the job.
Exactly. And it's important to remember that newer clocks generally complement rather than replace older ones. Researchers often use a suite of clocks because each might tell a slightly different yet equally valid story about an individual's aging process. For instance, an intervention might successfully lower an individual's grimmage, indicating reduced risks, and their Duden pace, indicating a slower rate of aging, yet surprisingly, their original Horvath chronological age might remain relatively unchanged. Each clock provides a distinct piece of the complex puzzle of biological aging.
So in essence, we have the first generation, the chronology predictors, like Horvath's clock, which are excellent for telling you how old your epigenome looks. The second generation, the outcome predictors, such as PhenoAge and Grimmage, are designed to tell you your risk for disease and mortality. And the cutting-edge third generation, the pace of aging measures like Duden pace, are explicitly built to assess how fast you are aging, which is critical for evaluating interventions. Each serves a unique and valuable purpose. #reliability, repeatability, and technical pitfalls of clocks. As exciting as these measures are, we have to talk about something fundamental to any scientific tool: reliability. How robust are they? If you took a biological age test today, and then again next week, without any major life changes, will the result actually be the same?
That's an absolutely critical question. And frankly, early epigenetic clocks did face significant challenges with technical noise and variability. It was an alarming reality that had to be addressed.
How bad was it?
Well, in the early days, due to factors like inherent measurement error on the microarray platforms used to read DNA methylation, subtle differences in how samples were processed, or even minor shifts in the proportions of different blood cell types within a sample, the same blood sample tested twice could yield biological age estimates that differed by as much as 9 years.
9 years?
Yeah.
From the same sample? Wow.
Exactly. Imagine getting a test back that tells you you're biologically 50 one week, and then from the exact same blood sample, it says you're 59 the very next week. That level of inconsistency is obviously a significant barrier to clinical utility. Such poor test-retest reliability could easily lead to false alarms, causing unnecessary anxiety, or conversely, it could completely obscure true biological changes, making it difficult to assess the impact of an intervention.
So how do they fix that?
Fortunately, the field recognized this limitation and has made tremendous efforts to improve precision. A particularly successful approach, pioneered by Levine, Higgins-Chen, and their colleagues, involves using principal component PC analysis to create what they call PC clocks.
PC analysis. What does that do?
Instead of using raw CPG readings, which can be noisy, they first perform principal component analysis. This statistical technique captures the dominant, most stable methylation patterns and effectively filters out a lot of the background noise. By training the clock on these more robust principal components, the result has been a dramatic improvement. Replicate tests now typically agree within less than 1 year of age difference.
Less than 1 year. That's a huge improvement.
It represents a dramatic increase in our confidence. As one researcher put it, with these methodological improvements, a person's longitudinal clock change is far more likely to reflect true biological aging rather than technical noise. This is a massive step forward, making these clocks far more suitable for tracking real changes over time.
Okay, so noise is less of an issue now. What else affects reliability?
Another significant factor that needs careful management is batch effects and platform differences. Most epigenetic clocks are trained and run on specific array platforms, like the older 450K methylation arrays or the newer, higher-density 850K EPC arrays. If you take the same sample and test it on 2 different array platforms, or even run it in different laboratories, the results can show slight but noticeable shifts.
So results aren't always comparable between labs or tests.
Not directly, without careful consideration. This means that absolute numbers from different sources or labs aren't always directly comparable. To mitigate this, researchers are implementing strategies such as restricting their analyses to only the most reliable and consistently measured CPG sites and employing mathematical cross-calibration techniques to standardize results across platforms. Metrics like intra-class correlation, ICC, are now commonly used to quantify a clock's reliability, with a high ICC, close to 1.0, being highly desirable, especially if these clocks are ever to be used in clinical settings.
Makes sense. What about different parts of the body?
Good point. Then there's the nuance of tissue specificity. It's not a universal number across your whole body. While Steve Horvath's original clock was truly remarkable for its ability to work across multiple tissue types, many later clocks are intentionally tissue-specific, such as a dedicated skin and blood clock for better accuracy within those particular tissues.
Okay, so blood age might differ from skin age.
Potentially, yes. And a fascinating and often confounding factor is the cell type composition within blood samples. As we age, the proportions of different immune cells in our blood naturally change. For instance, we tend to have fewer naive T cells and more memory T cells as the years go by.
The mix of cells changes.
Exactly. And here's a striking finding. A recent study revealed that naive immune cells appear epigenetically younger than memory cells by 15 to 20 years within the very same individual.
15 to 20 years younger within the same person.
Yes. This means that if an older person's blood sample reads as older, it might partly be due to a natural shift in their cell mix. They simply have a lower proportion of those epigenetically younger naive T cells.
So the changing cell mix messes with the reading.
It can confound it. To address this, researchers have developed concepts like intrinsic epigenetic age, exemplified by the intrin clock. The goal of intrin clock is to disregard these shifting cell counts and instead isolate the cell intrinsic aging changes the aging that happens within the cell, regardless of its type or proportion in the blood.
Trying to get at the aging inside the cell.
Precisely. The intrin clock is carefully calibrated to ensure that if you take different purified cell types from the same person, say, a T cell and a B cell, they will yield the same estimated age. This significantly isolates the true fundamental aging signal, making the clock more robust and interpretable. This evolution showcases the field's commitment to creating truly reliable and meaningful tools.
Okay, that makes sense. What about short-term changes if I test myself month to month?
Right. Finally, we need to set appropriate expectations for repeatability over short intervals. Given that aging is generally a slow, gradual process, most clocks typically stay quite flat over short periods, like a few months. You wouldn't expect a drastic change in your biological age from one month to the next.
Aging is slow, so the clock should be stable short-term.
Generally, yes. However, it's worth noting that some of the more sensitive clocks, particularly the third-generation pace clocks like Dundon Pace, might show small, genuine shifts even over a few months if a very strong intervention is in play. The important warning here is that a drastic change, say a 5-year reduction in epigenetic age over just 1 month, is highly unlikely to represent genuine biological rejuvenation. It's far more probable to be either technical noise or a transient, acute physiological effect that rapidly normalizes.
So the takeaway here is what practically, for the listener who might be looking at one of these tests, how should they interpret short-term changes?
The crucial message is that not all clock readings are gospel. While the technology is rapidly improving, it's vital to maintain a discerning eye. Always ask critical questions. Was the observed change larger than the known technical noise for that specific test? Has the change been replicated in follow-up measurements? Are we even looking at the right tissue or cell type for the question at hand?
Be critical of the numbers.
Exactly. The good news is that the scientific field is intensely focused on addressing these very concerns, constantly refining methodologies. As Dr. Morgan Levine aptly cautioned, while epigenetic clocks show a lot of promise as biomarkers of aging, we need to continually work to make these measures more reliable and valid if we want to someday use them to test interventions. The vision is for biological age tests to reach the reliability of something like a cholesterol test, a standard clinical measure. We're definitely getting there, but we aren't fully there yet. Hashtag what clocks tell us and what they don't.
That's fascinating how much the underlying tech has improved. So we've explored how these clocks work. But the real excitement, I imagine, comes from what they can actually tell us about our future, right? What makes them such compelling tools for understanding our health trajectory?
Absolutely. The fundamental reason for the enthusiasm is their remarkable predictive power. These sophisticated biomarkers manage to condense a vast amount of complex biological information into a single, often interpretable number that correlates significantly with critical health outcomes.
So what's the main thing they predict?
First and foremost, they tell us about risk of disease and death. There is now extensive and robust evidence showing that individuals with an accelerated epigenetic age, meaning their biological clock runs faster than their chronological years, consistently face a higher risk of developing a wide range of age-related diseases and, tragically, experience earlier mortality.
Higher biological age, higher risk?
Correct. For instance, large-scale meta-analyses have consistently found that each 5-year increase in epigenetic age is associated with a significantly elevated risk of all-cause mortality.
And you mentioned Grimmage before.
Right. To illustrate, let's revisit Grimmage. As we discussed, it was meticulously designed to predict mortality. And it does so with incredible accuracy, and not just for all-cause mortality, but for specific major age-related conditions like cardiovascular disease, various forms of cancer, and even lung fibrosis. What's more, Grimmage often outperforms traditional, well-established risk factors in predicting who will develop multimorbidity, which is the presence of multiple chronic diseases.
Better than some standard risk factors.
In some prediction contexts, yes. Similarly, a high proteomic age or a fast Dundon Pace score has been clearly linked to worse long-term outcomes, including a higher likelihood of cognitive decline, increased disability, and even observable midlife brain atrophy. In essence, these biomarkers pack a significant amount of prognostic information. They're likely reflecting the accumulated molecular damage and chronic physiological dysregulation that ultimately drives the onset and progression of chronic diseases. In that sense, they serve as powerful early warning signals.
Okay, so predicting risk is huge. What else do they reflect our lifestyle?
They do. Secondly, clocks also provide insight into their association with lifestyle and exposures. They capture, to a measurable extent, the impact of various lifestyle choices and environmental exposures on our bodies. A classic example is smoking. Smokers consistently exhibit faster epigenetic aging.
We see that with the twin study example.
Yeah, exactly. A compelling twin study directly demonstrated this, showing that the twin who smoked consistently had a higher DNA methylation age compared to their non-smoking identical sibling. This provides a clear internal control that highlights the impact of this particular exposure.
What about things like diet and exercise?
Those two. Beyond smoking, poor diet, insufficient physical activity, and exposure to environmental pollution have all been linked to accelerated clocks. Conversely, engaging in healthy behaviors consistently associates with more youthful biological profiles. Another twin study, for example, found that the more active twin had epigenetic signatures that correlated with lower metabolic risk than their less active counterpart.
Makes sense. The clocks reflect the impact of our choices.
They seem to capture the downstream effects of chronic inflammation, metabolic stress, and exposure to toxins on the epigenome. However, and this is a critical caveat we will explore further, correlation is not causation. These associations, while strong, don't necessarily prove that the clock causes these health outcomes, merely that it reflects them.
Right, that crucial difference again. Okay, what's the third big thing they tell us?
And this leads us to the third major area of utility, tracking intervention effects. This is where the profound hope for anti-aging therapies truly lies. The idea is that these clocks can serve as powerful, quantifiable readouts to assess whether a particular anti-aging therapy or geroprotector is actually working.
Testing if anti-aging treatments work faster.
Exactly. We have some intriguing early examples. A small but widely reported 2019 trial known as TRIME, thymus regeneration, immunorestoration, and insulin mitigation, utilized a unique drug cocktail comprising growth hormone, DHEA, and metformin. This trial reported an astonishing 2-year reduction in epigenetic age after just 1 year of treatment. This finding made significant headlines as potentially the first demonstrated reversal of epigenetic age in humans. While early, it was certainly a compelling signal.
2 years younger epigenetically in 1 year.
That was the claim, yes. Another pilot study in 2020 put a group of men on an 8-week lifestyle program that included specific dietary changes, regular exercise, and stress reduction techniques. This relatively short-term intervention resulted in an average 3-year decrease in their DNM age compared to a control group.
3 years younger from lifestyle changes in 8 weeks.
Again, that was the reported finding. More recently, data from the calorie trial, which studied caloric restriction, the undisputed gold standard anti-aging intervention in animal models, has also shown that caloric restriction effectively slowed epigenetic aging in humans.
So, CR slows the clock too.
It appears so. While these early results are undeniably intriguing, it's crucial to approach them with appropriate scientific caution, given the typically small sample sizes of these initial studies and the noise issues we discussed earlier with older clock methodologies. Nonetheless, they offer compelling hints that biological age might indeed be modifiable, and that these clocks provide a quantitative way to measure that change over a relatively short time frame, circumventing the need to wait decades for lifespan data to accrue, which is often impractical for clinical research.
So they're incredible predictors and responsive to our choices. But now we need to temper that excitement a bit. What are the crucial limitations? What don't these clocks tell us?
That's the critical flip side, because understanding the limitations is just as important as appreciating the strengths.
Okay, what's limitation number 1?
Firstly, clocks are not a direct mechanistic explanation. Epigenetic clocks are, by and large, phenomenological. This means they are mathematical constructs designed to identify patterns that correlate with aging, but they don't inherently explain why an individual is aging faster or which specific molecular or cellular processes are driving that acceleration.
They show the what, but not the why.
Pretty much. For example, if your Grimmage score is high, it certainly indicates a heightened risk, but that single number won't tell you whether that risk is primarily due to chronic unresolved inflammation or an accumulation of senescent cells or persistent glycemic stress or some other underlying factor. The clocks are built from changes across many CPG sites, each of which could potentially be influenced by diverse biological pathways.
Too complex to pinpoint one cause from the clock number alone.
Right. While recent research, including work from Morgan Levine's lab, suggests that clocks might consist of different modules, groups of CPGs that specifically track distinct aging pathways, perhaps some related to early development and others more acutely sensitive to stress, we are only just beginning the complex process of deconvolving these intricate relationships. In essence, clocks are biomarkers. They are not the essence of aging itself.
Biomarkers, not the root cause.
Exactly. They measure something that is strongly correlated with aging, but they are not proven to be the fundamental drivers of the aging process. So, If a treatment appears to make a clock appear younger, we cannot automatically conclude that it acted upon a fundamental aging mechanism. It might simply be masking a signal or influencing a downstream marker without affecting the core process. As one viewpoint insightfully noted, the time-dependent relationships between epigenetic clocks and health-related phenomena are complex and in need of further scrutiny. We must be vigilant not to conflate the map with the territory. The clock is a map, it's not the actual terrain of aging itself.
Okay, not mechanistic. What's the next big limitation?
This leads directly to the next, and arguably the biggest, caution. Clocks are not necessarily causal. Just because a higher biological age is statistically associated with worse health outcomes does not automatically mean that lowering that biological age will, by itself, cause an improvement in health outcomes or an extension of lifespan. It's the classic adage, association does not equal causation.
The gray hair example.
Exactly. Consider the analogy of gray hair. Gray hair is strongly associated with aging, but dyeing your hair back to its original color, while it might make you look younger, certainly won't make you physiologically younger or reverse any underlying aging processes. Similarly, we need to definitively determine whether changes in these biological clocks are drivers of the aging process, actively contributing to decline, or simply indicators, passive reflections of other damage that is truly driving aging.
Are they driving the bus or just passengers reporting on the journey?
That's a great way to put it. While there is some intriguing evidence that certain DNA methylation changes might indeed dysregulate genes in ways that contribute to aging, this remains an active area of research. Ongoing studies, for instance, use advanced statistical techniques like Mendelian randomization to try and establish causal links, examining whether genetically predicted epigenetic age actually causes specific diseases.
What are those studies finding?
Early findings from this type of research have been mixed. For example, one study found that grimmage acceleration might have a causal contribution to a higher risk of some cancers, but for other clocks, the causal links have been inconsistent or less clear. The field is actively working to untangle this complex relationship, but as of now, we don't fully know if reversing a clock will automatically translate to longer life or an extended health span.
Okay, so causality is still a big question mark. Any other major limitations?
Yes, finally, clocks are limited by what they're trained on. A clock's utility and the information it can provide are inherently constrained by the data it was trained with and the specific outcome it was designed to predict. A clock that was trained solely to predict chronological age, for instance, knows absolutely nothing about disease risk or health outcomes. It can tell you if your methylation profile looks older than your years, but not whether that older profile is good or bad for your health.
Garbage in, garbage out. Or maybe specific training in, specific prediction out?
More the latter. A mortality-trained clock, like grimmage, is excellent for risk prediction, but it might inadvertently overweight certain factors that were prominent predictors of mortality within its specific training data set, such as smoking, potentially underweighting other crucial aspects of aging, like, say, neurodegeneration, especially if the cohort it was trained on was primarily middle-aged.
So the training data shapes what the clock is good at predicting.
Absolutely. Furthermore, these clocks might miss entirely certain dimensions of aging that are not fully captured by DNA methylation changes. For example, some severe neurodegenerative processes, or the loss of muscle mass and strength, sarcopenia, might not be fully or accurately reflected in DNA methylation patterns found in a simple blood sample. This is why functional tests, assessments of physical strength, balance, cognitive function, and so on remain absolutely vital.
Can't just rely on the blood test clock.
No. We often emphasize that clocks measure what they were built to measure. Therefore, if you use a clock outside its intended context or purpose, its interpretation must be approached with considerable care and skepticism.
That brings us to a crucial point about interpretation. So what's the succinct summary of this duality between what clocks tell us and what they don't?
Aging clocks are powerful statistical predictors and undeniably useful biomarkers, but they are not crystal balls or magic buttons that can instantly reveal your entire future or unlock the secrets of immortality. They provide a probabilistic estimate of your aging status and your trajectory. They do not tell you with certainty, for example, you will get disease X at age Y, nor do they definitively reveal the underlying molecular cause of aging in any given person.
So use them carefully.
Exactly. It is absolutely essential that they be used in conjunction with and alongside other comprehensive medical assessments. And most importantly, any intervention that boldly claims to reverse aging based solely on clock readings must also demonstrate improvement in real, tangible clinical or functional endpoints. Without that parallel evidence, the reversal could be merely cosmetic, a change on paper that doesn't fundamentally alter the person's fate or health span.
Here's where it gets really interesting. We've just navigated the fascinating dual nature of these aging clocks. They are incredible predictors of disease and even respond to lifestyle changes, hinting at modifiability. But they also have clear boundaries. They don't give us mechanistic answers, and correlation is not causation. So, what's the biggest lesson here for someone wanting to truly understand their biological age?
I think the biggest lesson is that while these clocks are incredibly powerful and provide unprecedented insights into our biological state, they are ultimately tools for probabilistic estimation, not absolute truths or causative agents in themselves. They tell you what is correlated with aging and disease, but not necessarily why or how to definitively change it at a fundamental level.
So critical interpretation is key.
Paramount. Always ask what the clock was trained on, what it actually measures, and whether its readings align with other, more direct measures of your health and function. Don't rely on a single number.
Now we come to what is arguably the hottest debate in this field. Whether manipulating a clock reading truly changes the underlying aging process itself, or if it's merely moving a marker on a complex timeline without altering the fundamental reality. This is where the concept of causal inference becomes absolutely paramount.
This is indeed the crux of the matter, and to tackle it, we need to explore scenarios where clocks and actual biological function can diverge. These instances serve as crucial negative controls, or, if you will, cautionary tales that highlight the complexities.
Okay, so when do the clocks get it wrong or tell only part of the story?
Let's first consider scenario 1, where the clock moves dramatically, but there's no corresponding functional improvement, or perhaps even a worsening of the individual's overall health. A compelling real-world example comes from bone marrow transplants. This procedure is sometimes performed on older leukemia patients where they receive hematopoietic stem cells, blood-forming cells, from a young, healthy donor.
Right, getting new stem cells.
Yes. What happens? Scientists have observed that the DNA methylation age of the patient's blood dramatically resets to that of the young donor. And this younger epigenetic age isn't transient. It persists for years.
So their blood clock becomes young. Does that mean they are young again?
Well, that's the critical point. The crucial implication here is that this doesn't mean the patient's entire body has suddenly become young. This is essentially a cell replacement in one specific tissue, the hematopoietic system, which produces blood cells.
So it's almost like getting a new, younger engine in an old car,
right,
but the rest of the chassis is still original. You might get better fuel economy, but it's not a brand new car, right?
That's a perfect analogy. While the patient's immune function might see some rejuvenation as a result of having younger, healthier immune cells, their other organs, their brain, their heart, their kidneys, and so on, remain old and continue to age chronologically. So a 60-year-old who receives a transplant from a 20-year-old donor might now have 20-year-old blood epigenetically, but they are certainly not 20 again in any holistic sense. We would label this a partial and critically an artificial rejuvenation of one specific system, not a reversal of whole body aging.
So the clock change was real, but didn't reflect whole body aging.
Exactly. This serves as a powerful cautionary lesson. It's theoretically possible to artificially lower a blood epigenetic age by methods that replace or select for younger cells, or even by certain drugs that change blood cell proportions without truly reversing the entire body's aging process.
Okay, that's a clear example. What else?
Another example comes from acute changes like sleep deprivation or acute stress. A single night of severe sleep deprivation or a period of intense acute stress can transiently alter DNA methylation patterns and cause a measurable spike in epigenetic age.
Your clock gets older from pulling an all-nighter.
It can appear that way temporarily. However, this spike rapidly normalizes once the individual recovers from the sleep deprivation or the stressor is removed. This doesn't mean you genuinely aged a year in one night and then magically reversed a year just by catching up on sleep. It means the clock is responsive to short-term physiological stressors.
So it's just a temporary blip.
Right. Imagine someone taking an epigenetic age test during an incredibly stressful week at work and then again after a restful 2-week vacation. They might indeed see a difference in their clock reading, but we wouldn't conclude that the vacation literally made them biologically younger in a lasting, fundamental way. It simply removed the transient aging acceleration caused by the acute stress. These are what we call negative controls. They demonstrate that while clocks are responsive to physiological changes, not every change reflects a permanent fundamental aging reversal. They show that clocks can be influenced by factors that do not equate to genuine, lasting aging changes.
Okay, so clocks can move without real aging change. What about the opposite? Can you get healthier without the clock noticing?
Yes, absolutely. Let's explore scenario 2, where functional health improves significantly, but the clock shows no change, or perhaps even goes the wrong way. This can be equally illustrative. Take exercise, for instance. It is unequivocally beneficial for health span, dramatically improving quality of life, and it very likely slows aspects of the aging process. Yet many studies don't find a large or consistent short-term epigenetic age difference in individuals who adopt exercise regimens.
So exercise is good, but doesn't always lower the clock age.
Not necessarily, or not always dramatically in the short term. In fact, intense athletic training can sometimes even transiently stress the body, leading to a slight temporary increase in certain inflammatory markers, or perhaps even a subtle uptick in epigenetic age, even though the long-term systemic effect of exercise is overwhelmingly positive.
So someone could be doing everything right, feeling fantastic, seeing real improvements in their physical health, but their epigenetic age test doesn't budge. That's a bit of a head-scratcher.
It absolutely is, and it's an important point of nuance. Imagine a scenario where someone commits to a rigorous 6-month strength training program. They undeniably become stronger, their cardiovascular health improves, their insulin sensitivity increases, and they subjectively feel biologically younger and more capable. Yet, if you were to measure their Horvath clock, it might remain stubbornly unchanged at, say, 55.
Does that mean the exercise didn't help their aging?
Not necessarily. It could simply mean that the specific aspects of aging that were improved, like muscle mass, neuromuscular function, or metabolic health, aren't comprehensively captured by that particular epigenetic clock, or that the clock's resolution or timescale is simply too coarse to detect a significant change over a mere 6 months.
The clock might just be missing those benefits.
It's possible. Another fascinating, albeit animal example, comes from the classical parabiosis experiments in mice. In these studies, an old mouse's circulatory system is surgically joined to that of a young mouse, leading to a shared blood supply. Remarkably, the old mice often show various signs of rejuvenation across different tissues.
Young blood helping old mice.
Right. However, Steve Horvath himself reported that in one such study, the epigenetic clock did not show a significant age reversal in the old mouse's brain after parabiosis, despite other measures hinting at improvements in other organs. This highlights that these clocks are one measure among many, and they might not reflect every facet of biological age change, especially in specific tissues or over short observational periods. It underscores the point that rejuvenation can be multifaceted and not uniformly reflected across all biomarkers.
So we've got these clear examples where clocks can be misled or don't tell the whole story. This brings us to a fundamental scientific rigor, doesn't it? How do scientists formally address this dilemma of correlation versus causation?
This is where the concept of surrogate endpoint validation becomes absolutely crucial. The gold standard in medical science, particularly for regulatory bodies like the FDA, is known as the Prentice criteria for a surrogate biomarker.
Prentice criteria. Okay, what does that involve?
In simple terms, this set of criteria posits that for a biomarker to be considered a valid surrogate for a clinical outcome, two things must be true. First, the biomarker itself must be a reliable predictor of the clinical outcome. And second, if an intervention truly affects the clinical outcome by acting through that biomarker, then any observed difference in the clinical outcome should be fully accounted for by the changes in that biomarker.
Okay, can you break that down a bit?
Let's put this in layman's terms. If lowering your epigenetic age is truly a causal pathway to improved health span and longevity, then any therapeutic intervention that successfully lowers your epigenetic age should also consistently lead to better health outcomes and longer life. And conversely, if an intervention fails to lower the epigenetic age, it should not yield significant benefits on aging outcomes.
So the clock change has to directly track the health outcome change for it to be causal.
Essentially, yes, for it to be a validated surrogate. So what is the current status for aging clocks against this stringent standard? The candid answer is that this level of rigorous proof has not yet been definitively demonstrated for any aging clock to the standard needed for full regulatory acceptance as a primary surrogate endpoint.
Not proven yet.
Not to that level. Achieving this would require numerous large-scale, meticulously designed, randomized controlled trials. These trials would need to consistently show that interventions capable of reducing, for example, grimmage or Dundon pace, also reliably delay the onset of age-related diseases and extend lifespan. And, just as importantly, they would need to show that interventions that do not change the clock also do not produce significant health benefits related to aging.
That sounds like a huge undertaking.
It is. Currently, we have what could be described as a patchwork of suggestive evidence. For instance, the calorie trial, studying caloric restriction in humans, showed promising results. It slowed epigenetic aging and also improved various metabolic risk factors. This is a positive alignment. However, there are also numerous supplements or drugs that claim to reduce epigenetic age in small pilot studies, but for these, we currently lack definitive proof that such clock changes translate into real-world reductions in disease or improvements in health span. Therefore, and this is a critical point, until such causal links are rigorously proven, clocks remain unvalidated surrogates. It's certainly possible that with future validation or further refinement of the clocks themselves, this status could change.
So given this nuanced picture, what's the most practical guidance for our listeners when they encounter claims about biological age or consider taking a test?
The crucial implication for anyone interpreting these results is to look at the whole picture. Do not fixate on a single number. If, for instance, a biological age test reports that your biological age dropped by 5 years after participating in a new diet or exercise program, it's imperative to also ask, did your blood pressure improve? Did your cholesterol levels get better? Did your physical fitness, strength, or endurance measurably increase? How about your mood and energy levels?
Look for real-world changes, too.
Absolutely. If these real-world health indicators also show clear improvement, then the change in the clock reading likely reflects something genuine and meaningful. However, if only the clock moved, but nothing else did, no functional improvements, no better lab results, then you should approach that result with a healthy dose of skepticism. It could simply be what we might call a placebo effect on paper.
And what if you feel better, but the clock didn't change?
Conversely, the opposite scenario is also informative. If you feel significantly healthier and your doctor objectively notes improvements in various health parameters, but a specific biological clock didn't change, it doesn't necessarily mean the intervention failed. It might simply mean that particular clock isn't designed to capture those specific improvements, or its sensitivity is not attuned to the kind of change you experienced. It reinforces that a single number cannot fully encompass the multifaceted nature of human health and aging.
This brings us to an immense potential, one that could truly accelerate how we develop new therapies. Why wait 10 or 20 years for survival data in clinical trials if a reliable clock readout in just 6 months could tell us the likely long-term outcome? This is the promise of using aging clocks as surrogate endpoints. What's the regulatory landscape here, particularly from bodies like the FDA?
The potential for using aging clocks to accelerate clinical trials is indeed enormous, and it's a driving force behind much of the research. However, regulators like the FDA set an exceptionally high bar for surrogate acceptance. It's a rigorous process, and for good reason.
Why so high?
Well, historically, accepted surrogate biomarkers think of things like cholesterol levels for heart disease risk, or HbA1c for predicting diabetic complications, only achieved approval after robust, irrefutable evidence demonstrated that changes in that biomarker reliably and consistently predict corresponding changes in hard clinical outcomes, such as heart attacks, strokes, or kidney failure. Many promising biomarker candidates, even those that show strong correlations, ultimately fall short of the stringent standard.
So the proof has to be really strong.
Extremely strong. For an epigenetic clock to be an approved surrogate for, say, aging itself, or for a complex composite of age-related diseases, developers would need to demonstrate through multiple clinical trials that interventions which successfully slow the clock also demonstrably reduce disease incidence and mortality. Furthermore, they would need to show that interventions failing to slow the clock do not yield significant benefits on those same aging outcomes. This is a formidable challenge demanding multiple large-scale clinical trials and a profound causal understanding of the pathway from biomarker change to clinical benefit.
That sounds like a lot to prove.
It is. As one paper clearly noted, FDA acceptance of a surrogate endpoint is considerably challenging, emphasizing that biomarkers must be proven reliable, reproducible, and meaningfully predictive of the clinical outcome. The FDA does have a biomarker qualification program, which provides a pathway for qualifying biomarkers for specific contexts of use. However, to date, no epigenetic clock has yet successfully gone through this formal qualification process for an anti-aging indication.
So no clock is officially approved as a surrogate for aging yet.
Not yet. That being said, it's important to remember we're still in the relatively early days. Geroscience trials, which are clinical studies specifically designed to target fundamental aging processes rather than just individual diseases. An excellent example is the TANG trial, which stands for Targeting Aging with Metformin, are currently underway.
The TANG trial, right. What are they measuring?
These trials primarily use traditional clinical outcomes, such as the onset of chronic diseases, as their primary endpoints. However, crucially, researchers in these trials are also meticulously collecting biological samples specifically to measure biological age using various clocks. These studies are poised to provide the first real test of the causal link between clock changes and hard outcomes.
So TAME could give us key data.
It really could. If, for instance, metformin is shown to slow the accumulation of age-related diseases in the TAME trial, and concurrently it also slows epigenetic aging measures compared to placebo, that would significantly strengthen the case for these clocks having a causal link to aging and disease. If not, it raises important questions either about metformin's mechanism or the specific clock's relevance.
Is there a middle ground for using clocks in trials now?
Yes, some scientists have proposed a pragmatic middle ground, using clocks as secondary or exploratory endpoints in trials. This approach allows researchers to build an evidence base over time without necessarily relying on the clock as the primary measure for drug approval. Regulatory bodies, in turn, might consider conditional acceptance for highly predictive clocks based on shorter-term data.
Conditional approval. It's like, okay for now, but keep tracking.
Exactly. This could potentially allow for faster therapy approval, but it would typically come with the requirement for continued tracking of true hard clinical outcomes post-approval to confirm the long-term benefit.
And what about the whole idea of treating aging itself?
That's another important regulatory nuance. The FDA at present does not approve drugs specifically for aging itself. Their focus remains on specific diseases or conditions. So while a clock could be qualified as a biomarker of aging, it might not be an approved surrogate endpoint unless the indication is framed around a concept like reduction of multimorbidity, reducing the risk of developing multiple chronic diseases, or a specific age-related condition. And yes, as you hinted, we will delve much deeper into the complexities of biomarker qualification and surrogate criteria in a future deep dive, episode 11 of this series.
So the bottom line here is that while the promise is immense, we're not quite there yet in terms of regulatory acceptance. Sounds like a complex path forward.
Precisely. We're not quite there yet in using biological age as an accepted primary medical outcome or a validated surrogate endpoint in clinical practice. It will require considerably more validation, standardization across different platforms and labs, and a robust scientific consensus on what constitutes a truly meaningful change in a biological age reading. It is an active frontier of research and development, and the coming years will undoubtedly see pivotal studies that clarify whether epigenetic clocks can truly stand in for the hard clinical endpoints of aging.
But people are working on it.
Oh, yes. Groups like the Clock Foundation and various academic consortia are actively working to amass the necessary data to convince regulators. Researchers of the new unpack MRI clock, for instance, explicitly stated their belief in its potential as a practical, quick method to determine efficacy in trials for anti-aging therapies. The potential is clear, and the scientific community, including regulators, are excited by it, but they will demand rigorous proof before broad adoption.
That's a crucial perspective on regulatory hurdles. Given the complexity of aging as a multi-system process, it suggests that relying on a single biomarker, no matter how good, might give us an incomplete picture. This brings us to the concept of triangulation. What does that mean in the context of measuring biological age?
You've hit on a core principle that the field is increasingly embracing. While DNA methylation clocks have, understandably, taken center stage due to their initial breakthroughs, aging is inherently a complex, multi-system biological process. To truly capture its essence, relying on a single type of biomarker can indeed provide an incomplete or even misleading picture. This is precisely why researchers are strongly advocating for triangulating biological age with multiple modalities. It's about looking at the same phenomenon from different independent angles.
Using multiple types of clocks and measures together.
Exactly. Let's delve into the various modalities that can be combined. Beyond DNA methylation, we have, as previously mentioned, proteomic and metabolomic ages. Proteomic clocks, for instance, analyze the vast array of proteins in your blood. These proteins are the functional workhorses of your cells, carrying out most biological processes.
We talked about those earlier.
Right. A powerful example is the proteomic aging clock, PACE, which was developed using data from nearly 3,000 different proteins in over 45,000 individuals. This clock demonstrated that individuals whose proteomic age was lower than their chronological age tended to perform better on cognitive tests and had a lower overall risk of disease. More recent work, like a Nature Medicine study, identified a set of 204 key proteins that could predict a person's age, and remarkably, predict the incidence of 18 different chronic diseases and all-cause mortality across diverse populations.
So proteins give a different powerful signal.
They do. The key insight here is that unlike methylation, which primarily regulates gene activity, changes in the proteome might be more directly linked to functional changes within cells and could potentially highlight more direct drug targets.
And metabolomic clocks.
Metabolomic clocks analyze the metabolome, the entire collection of small molecules, such as sugars, fats, and amino acids that are present in your blood. These metabolites are the direct outputs of cellular metabolism and shift in predictable ways with age. Specific patterns of metabolites, like the ratios of certain amino acids or lipids, can be used to create a metabolic age predictor. These clocks are valuable because they might capture aspects of aging missed by other modalities, such as nuances of mitochondrial function or even the complex contributions of your gut microbiome to your overall health and aging.
So different omics give different clues. Are people combining them?
Yes, there's a growing trend towards creating composite biomarker indices. This means combining different types of biomarkers into what some call a superclock or a comprehensive biological age scorecard. For example, you might integrate an individual's epigenetic age, their proteomic age, perhaps telomere length, though telomere length alone is a relatively weak and less predictive biomarker for individuals. It might offer specific information about cellular replicative history when integrated into a broader model, and various standard clinical measures into a single, overarching model.
Building a bigger picture with all the data.
Exactly. The idea is that each component adds a unique piece to the overall puzzle. Researchers, including Morgan Levine's group, are actively exploring these multi-omic models using advanced machine learning to maximize their predictive accuracy for heart health outcomes.
And we shouldn't forget the simpler stuff.
Absolutely not. Crucially, we must not forget the continued importance of phenotypic functional measures. These are the simpler, more directly observable measures that directly reflect an individual's physical and cognitive capabilities and their vulnerability to aging. Think about gait speed, which in older adults is an incredibly powerful predictor of mortality, sometimes even called the 15-second aging test.
How fast you walk tells a lot.
It really does. Other vital functional measures include grip strength, lung capacity, and cognitive performance. A truly comprehensive assessment of biological age must include these phenotypic markers, as they are the direct outputs of the aging process and reflect real-world health. Some frameworks even propose using a frailty index, which is based on the accumulation of health deficits, as another measure of biological age. While physical frailty and epigenetic age are correlated, they are not identical, and using both together significantly enriches our overall assessment.
And imaging, too, like the brain scans.
Yes, and of course, as we discussed earlier, imaging and organ function tests remain vital. We talked about MRI brain age, but similar measures exist for other organs. Cardiac age can be inferred from vascular imaging or coronary calcium scores, bone age from bone density scans, and immune age from detailed analysis of T-cell receptor diversity. The overarching goal is clear. If an intervention claims to reverse aging, we would ideally want to see multi-organ benefits reflected across various imaging and functional tests, not just an improvement in a single isolated metric.
So the core concept here is that if we look at a wide array of these measures, we get a much clearer, more confident picture. It's like using multiple GPS satellites to pinpoint your exact location.
That's an excellent analogy. The central premise of triangulation is that if multiple independent measures coming from different biological levels and methodologies all concordantly indicate an aging slowdown or reversal, then our confidence in the reality and robustness of that effect increases significantly.
If everything points the same way, you can trust it more.
Exactly. For example, if an individual undergoes an intervention and subsequently their epigenetic age is lower, their proteomic age is lower, their inflammatory markers have improved, and their physical performance shows clear gains, all these converging lines of evidence collectively paint a highly convincing picture of a true holistic anti-aging effect.
And if they don't agree?
Conversely, if only one measure shows a change while all the others remain static or even diverge, then considerable caution is warranted in interpreting that singular result. This multimodal approach also offers profound mechanistic insight. Different modalities can hint at why someone might be aging faster.
Like figuring out the main driver for that person.
Potentially. For example, a proteomic clock might highlight unusually high levels of specific inflammatory cytokines, such as CXCL9, which a Stanford-led study strongly associated with biological aging and functional decline. This suggests that inflammation might be a primary culprit for that particular individual, opening the door to highly targeted interventions that specifically address inflammation. Similarly, a metabolomic signature might point directly to issues like insulin resistance or oxidative stress as key factors. By looking at the individual components of these sophisticated clocks, the top proteins, metabolites, or CPG sites involved researchers can often link them back to established hallmarks of aging and specific biological pathways, like cellular senescence or autophagy.
So for our listener, what's the practical implication of all this multimodal thinking?
The practical implication is that we are definitely moving towards the era of personal aging profiles. This envisions a future where robust estimates of your biological age come from a combination of blood tests, advanced imaging, and other assessments. Currently, standardization is still lacking across the various commercial and research offerings. One company might provide you with a DNA methylation age and a telomere length, while another might give you a proteomic age.
So it's not quite like a standard blood panel yet.
Not yet. But imagine a future where your annual physical might include a comprehensive suite of aging measures, much like a standard lipid panel already includes HDL, LDL, and triglycerides to give a multifaceted view of your cardiovascular health.
What should people do now then?
For now, when you're evaluating any anti-aging strategy or trying to assess your own personal risk, it is incredibly wise to adopt this multimodal mindset. Don't hang your hat on a single number. If an epigenetic test suggests you are biologically older than your chronological age, cross-check that with other indicators. Does your blood pressure align? Are your chronic inflammation markers elevated? How about your aerobic capacity and overall physical fitness? Discrepancies between these different measures can also be incredibly informative. They might tell you where a particular clock is more or less sensitive, or where your unique aging trajectory is manifesting most clearly. Ultimately, aging is a profoundly complex process, so relying on a broad toolkit of assessment will give you the most accurate navigational fix on where you stand.
This raises an important question. If aging is so complex, how can a single number capture it? What we've discussed highlights that while each clock offers a piece of the puzzle, the real power comes from combining these different lenses, from our epigenetics to our proteins and physical performance, to get a truly holistic view of our biological age.
Absolutely. The multimodal approach acknowledges the multidimensional nature of aging. It's about leveraging the strengths of each clock type and functional measure and using their convergence or divergence to build a more robust, reliable, and ultimately more actionable understanding of an individual's biological age and their unique aging pathways. It moves us beyond a single number to a comprehensive biological portrait.
So we've explored the immense promise and the scientific intricacies of these biological age clocks. But let's be honest, there's also been a significant amount of hype surrounding biological age testing, with bold claims of reversing aging by X years popping up everywhere. It's absolutely essential that we now inject a healthy dose of skepticism into this discussion.
You're absolutely right. With any rapidly advancing scientific field that holds such profound implications for human health, hype is an unavoidable byproduct, and it's crucial to examine the limitations and failures that often receive far less attention than the success stories.
Like what kinds of failures?
Well, one major issue is null results and publication bias. Not every single intervention, even those widely believed to have anti-aging effects, consistently moves these biological clocks. We primarily hear about the success stories because they are published in prominent journals and subsequently publicized by research institutions or companies. But what about all the cases where an anti-aging supplement or a specific treatment showed absolutely no effect on biological age markers?
We don't hear about those as much.
Exactly. Those are equally, if not more, important for a balanced scientific understanding. For example, many individuals take NAD plus precursors, such as nicotinamide riboside, NR, or nicotinamide mononucleotide, NMN, with the hope of slowing aging. Yet, to date, the evidence for them causing a significant reduction in epigenetic age remains unclear or, at best, minimal. And critically, these null results are seldom trumpeted in press releases.
A follow-through problem.
That's it. This phenomenon is often referred to as the file drawer problem, where studies that yield negative or null results are less likely to be published or widely disseminated, thereby skewing the overall perception towards success stories. It is absolutely crucial for the scientific field to report and rigorously examine these failures. If an intervention doesn't change the clock and doesn't improve a person's function, that's a valuable finding. It tells us that the intervention wasn't effective. Conversely, if an intervention doesn't change the clock but does demonstrably improve function, that's also incredibly illuminating, as it tells us something important about the limitations of that specific clock and what aspects of aging it might be missing.
Okay, so publication bias is one thing. What else?
Then there are what we can call false starts. Early epigenetic clock research, driven by intense excitement, did see some instances of overinterpretation. There were cases of small pilot studies claiming very significant age reversal that later drew criticism for methodological issues or overly optimistic conclusions.
Like the TRIUM trial or the lifestyle study you mentioned.
Potentially, yes. For example, the 8-week lifestyle trial we mentioned earlier, which reported a 3-year epigenetic age reduction, was certainly intriguing. However, skeptics rightly pointed out that it was a very small study, with only about 18 participants per group, and that the specific clock used, Horvath's original clock, may not have been optimally suited to detect such short-term, nuanced changes. Similarly, the TRIUM drug trial, while generating immense excitement, only included 9 participants and, critically, lacked a control group.
So small studies, maybe not the best clock, no control group, need caution.
Exactly. While the results were certainly exciting and pointed towards a potential avenue of research, we had to be very cautious about drawing sweeping conclusions from such preliminary data. The risk here is that the public and even researchers can jump to conclusions based on early, unconfirmed results, leading to potentially misguided expectations.
What if different clocks give different answers?
That's another common practical issue. Clocks disagreeing. If you run multiple biological clocks on the same individual at the same time, they won't always tell the exact same story. One clock might show a 2-year reduction in biological age, while another might remain unchanged or even show a slight increase, all from the same intervention or in the same individual.
So you could cherry pick the result you like.
Potentially, yes. This phenomenon was actually observed in the TRIUM trial itself. They measured multiple epigenetic clocks, and while some did show significant changes, like the phenoage and Horvath clocks dropping, other clocks showed much less movement. When researchers or companies selectively highlight only the clock that showed the most favorable result, it can be very misleading. A comprehensive analysis of all relevant clocks is needed to reveal a more complete picture of what aspects of biological age might have truly changed. If only one proprietary clock, perhaps a company's in-house algorithm that lacks external validation, shows a dramatic youthening, while other well-established clocks do not, you should be very wary of the accompanying hype.
Okay, makes sense. What about the clocks themselves? Are they all equally good?
Not necessarily. We also face challenges with overfitting and generalizability. There is an ever-growing list of clocks being developed, some built on relatively small data sets or very specific populations. Not all of these have been rigorously validated externally. A clock might appear to work exceptionally well in the specific study where it was developed, but when it's tested in a different cohort, perhaps one with different demographics, health statuses, or ethnic backgrounds, it might significantly underperform.
Works in one group, fails in another.
It can happen. We saw this with some of the earlier clocks, for example, which didn't generalize well to individuals of non-European ancestry or to very old ages. The scientific community has largely recognized this limitation, and newer, more robust clocks, such as Dundin pace and the proteomic clocks, have been explicitly tested and validated across multiple diverse cohorts and ethnic groups. However, for any user, a crucial question to ask is, has this clock been validated in people like me? It's critical to warn against using a clock that was, for example, trained exclusively on healthy 40-60-year-olds to interpret the biological age of a frail 85-year-old. The results in such a case would likely be unreliable.
Good point. And what about all those tests you can buy online now?
Right. Finally, we must address the widespread proliferation of direct-to-consumer tests and the potential for misinterpretation. A growing number of companies now sell mail-in biological age tests directly to consumers. While many of these are grounded in solid scientific methodologies, some may not adequately disclose their methods, their limitations, or the confidence intervals around their estimates. Consumers, often without a scientific background, may not fully understand these nuances or the fact that biological age is, at its core, an estimate, not a precise measurement like weight.
So people might take the number 2 literally.
There's a significant risk of overinterpretation. For example, an individual might panic if their result says biological age 65 when they are chronologically 60, internalizing a sense of doom, even though that 5-year difference might fall within the known test error margin or simply reflect a modifiable risk factor. Conversely, someone told they are biologically much younger than their actual age might become complacent, thinking, I'm 50 but my test says 40, so I'm fine. And, as a result, ignore real health issues like high blood pressure or prediabetes that need addressing. We must always remember that these tests are tools to guide health decisions, not final judgments on one's health or destiny.
So they need context.
Absolutely. An illustrative critical study titled Failed Tests of DNA Methylation Clocks specifically stress-tested clocks for weaknesses, pointing out that some early clocks could have low accuracy for comparing individuals of the same age and limited resolution for short-term changes. This type of self-critical research is incredibly healthy for the field as it forces developers to constantly strive for improvement and helps prevent blind faith in the numbers.
So the overarching message here is that while the science is moving fast, it's crucial to remain grounded and realistic.
Absolutely. While we are incredibly optimistic about the future of measuring biological age and its potential applications, it is profoundly wise to maintain scientific skepticism. Approach any grand anti-aging claims with significant caution until they have been rigorously replicated in independent studies. Always demand to see multiple lines of evidence, ideally utilizing the multimodal measures we discussed earlier to corroborate any claimed changes. Recognize that we are still in the early stages of truly understanding how to interpret and apply these powerful tools. Aging is an extraordinarily multidimensional biological process, and it is unlikely to be reducible to a single, simple metric, much like your credit score doesn't encapsulate your entire financial reality. The promise of these clocks is undeniably real, but so are the scientific challenges and the responsible use challenges in applying them correctly and ethically. #ethical considerations of age scoring.
That's a vital dose of skepticism. Now let's transition from the purely scientific and technical aspects to something equally profound. The ethical and social implications of assigning individuals a biological age. This isn't just a number. It could have far-reaching societal consequences.
You've hit on a crucial point. Beyond the scientific validity, the act of assigning someone a biological age, especially if it deviates significantly from their chronological age, opens up a complex array of ethical concerns.
Like how people might feel about getting that number.
Exactly. First, consider the psychological impact. Learning that your biological age is significantly higher than your chronological age could trigger intense anxiety, profound stress, or even a sense of fatalism. Imagine a 40-year-old being told they have the biological body of a 55-year-old. This could lead to despair, a sense of accelerated decline, or even a feeling of why bother trying if I'm already old. Such a revelation could potentially become a self-fulfilling prophecy if it demotivates individuals from pursuing healthy behaviors.
Or the opposite, right? Complacency.
Precisely. Conversely, someone who is told they're biologically much younger than their actual age might develop a false sense of complacency, leading them to become overconfident about their health and potentially ignore genuine health risks. This situation is akin to genetic testing for disease risk. Not everyone reacts to such information in the same way, and not everyone may even wish to know. Therefore, proper counseling and clear, sensitive context are absolutely crucial when delivering such results to avoid misinterpretation and undue psychological distress. It must be strongly emphasized that biological age is modifiable, and a higher reported age should be viewed as a call to action, an opportunity for intervention, not a death sentence.
Okay, psychological impact is huge. What about privacy?
A major concern. Next, there are serious concerns regarding privacy and discrimination. Biological age data is inherently highly personal and sensitive. A significant risk arises if employers or insurance providers gain access to an individual's aging biomarker results. Could this lead to new forms of discrimination?
Like charging older biological ages more for insurance.
Exactly. For example, a life insurance company would understandably have a strong financial interest in knowing if an applicant's epigenetic age is significantly higher than their chronological age, as this could imply a substantially higher mortality risk. While some countries have laws protecting genetic information in insurance underwriting, it's currently a legal gray area whether these protections would extend to epigenetic or other biomarker data that reflects biological age.
So the laws might not cover this yet.
It's unclear. There is genuine concern that without clear regulation, epigenetic tests could be misused in insurance or even employment decisions, creating a new form of ageism or health-based discrimination. Imagine being in perfect health but facing significantly higher insurance premiums or being denied certain job opportunities simply because a test indicates an older biological profile. This would be profoundly controversial and arguably unjust, especially given the inherent imperfections and error margins of current tests.
That sounds deeply unfair. What about consent?
Another critical area: consent and understanding. If these tests become commonplace, ensuring that individuals truly understand what is being measured, what the results mean, and what their implications are is paramount. A controversial application arose in some jurisdictions where proposals were made to use bone age or epigenetic tests to verify the age of refugees or unaccompanied minors, for instance, to determine if they are genuinely under 18.
Using these tests for legal age verification.
Yes, and beyond the purely technical accuracy issues, epigenetic clocks, particularly for age estimation, have inherent error margins that could lead to the misclassification of a minor as an adult or vice versa. There's a profound ethical issue in using such tests on vulnerable individuals who may not be able to fully consent or grasp the long-term implications of these results.
And how might the public misuse this information?
Well, we also need to consider the potential for overinterpretation by the public. We live in a society that often places a high premium on youth, and there's a legitimate worry about the rise of an epigenetic age obsession. People might begin comparing their biological ages competitively, leading to undue pressure to lower their numbers at all costs. This societal pressure could, in turn, fuel the aggressive marketing of anti-aging products, some of which may be entirely pseudoscientific, preying on anxieties.
Treating it like a score to beat.
Exactly. It is crucial to maintain a balanced perspective. Biological age is merely one aspect of a person's overall health, not a definitive score of their worth or something to optimize to an arbitrary maximum. For example, an individual might have a higher biological age due to a past severe illness or an unchangeable genetic predisposition, despite doing everything right in terms of lifestyle. Such individuals should not be stigmatized or made to panic.
How should doctors handle this?
That's the final key area: ethical use in medicine. If a doctor obtains a patient's biological age, how should this information inform their care? Could it be used as a powerful motivator for behavioral change? For example, a doctor might say, "Your tests indicate you're biologically 10 years older. Let's work on reducing that by tackling your blood sugar and weight." This could be a positive and empowering use if handled properly.
But it could also backfire.
Yes. There's also the potential for fostering nihilism, where a patient might think, "I have the biology of an 80-year-old at 65. No wonder I feel lousy. There's nothing left to do." Medical professionals will absolutely require constructive guidelines on how to integrate such nuanced and potentially emotionally charged information into patient care, much like the careful handling and counseling provided for genetic testing results for conditions like BRCA mutations or APOE status.
So the message here is that while the science pushes forward, we also need a parallel, robust conversation about responsible development and application. It's not just about what we can do, but what we should do.
Exactly. The call is for responsible innovation. Several reports on epigenetic age tests have already stressed the paramount importance of rigorous validation, complete transparency regarding methodologies and limitations, and the urgent need for ethical guidelines to guard against privacy risks and potential misuse. Some have even suggested the development of formal certification or standards for consumer-facing biological age tests to ensure quality and clarity in reporting results. Ultimately, the fundamental goal is to utilize this powerful biological age information to genuinely help people to personalize prevention and treatment strategies, to effectively motivate healthy lifestyle changes, and to quantitatively measure progress, all without inadvertently causing harm or exacerbating existing social inequities. As the science continues its rapid advancement, parallel discussions in bioethics and policy will be absolutely essential to establish the necessary boundaries for the fair and equitable use of these powerful new tools.
Okay, we've journeyed through the intricacies of biological age. We've seen the incredible potential of these clocks, from predicting future health to hinting at intervention success. But we've also navigated the crucial scientific and ethical minefields, the difference between correlation and causation, the pitfalls of technical noise, and the profound implications of age scoring for individuals and society. Now, let's synthesize what we've learned. For you, our listener, here's a flashcard summary of the key concepts and distinctions for retention.
Let's distill this into actionable takeaways. First, biological age versus chronological age. Think functional capacity versus just time lived. Next, clock generations. Remember, first gen for chronology, second for outcome risk, and third for pace of aging. Reliability matters. Early clocks had significant noise, up to 9 years, but PC clocks brought that down to less than 1 year. Huge improvement. Clocks as predictors. They're powerful for predicting disease, mortality, and reflecting lifestyle effects. But clocks, not causal. They're indicators, not proven drivers. Remember the bone marrow transplant or gray hair examples? Surrogate endpoint high H bar. Getting FDA approval as a true surrogate is complex and hasn't been met yet for aging clocks. Multimodal triangulation. The future is combining epigenetic, proteomic, metabolomic, functional, and imaging data. Skepticism essential. Be wary of hype, look out for null results, clock disagreement overfitting, and risks with consumer tests. And finally, ethical concerns. We must consider the psychological impact, privacy, potential discrimination, consent issues, and public overinterpretation.
That's a fantastic synthesis. Now, building on this comprehensive understanding, how can someone apply this practically? What's an actionable framework, almost an aging scorecard approach for evaluating an intervention or their own health?
An excellent question. When you're considering any intervention, be it a new drug, a specific diet, an exercise program, or a supplement purported to affect aging, or simply when you're seeking a comprehensive assessment of your own health, we recommend gathering a standardized panel of outcomes. Think of it as your personal aging scorecard.
Okay, what goes on this scorecard?
First, include epigenetic clocks. You'll want to utilize at least one well-validated second-generation clock, like PhenoAge or Groomage, to assess your biological age in years and your overall risk profile. And, crucially, include a pace measure, such as Dondon pace, to see if the intervention actually shifts your rate of aging.
Get both a snapshot and the speed.
Exactly. Second, always incorporate functional measures. These are your real-world health indicators. Test your physical performance, things like grip strength, walking speed, and balance. Also assess your cognitive function and other standard clinical indicators, such as blood pressure and glucose levels, for tangible, real-world improvements. These are direct measures of how your body is actually functioning.
Measure how you actually perform.
Right. Third, monitor laboratory biomarkers. Check relevant blood markers, such as inflammation markers like C-reactive protein, CRP, or interleukin-6, IL-6, metabolic markers, liver and kidney function tests, and your lipid profile. These often comprise part of what informs a phenotypic age, and they can confirm whether any observed clock change aligns with an improvement in fundamental risk factors.
Next to standard blood work, too.
Yes. Fourth, and critically, track safety metrics. Always monitor for any adverse effects or unintended trade-offs from the intervention. An intervention that dramatically lowers a biological clock but simultaneously causes other health issues or uncomfortable side effects is fundamentally problematic. The goal is health span, not just a number.
Safety first, always.
Always. Finally, embrace null and negative results. Be willing to acknowledge and report when nothing changes or when outcomes go against expectations. In science, knowing what doesn't work is just as vital as knowing what does.
So this scorecard forces a holistic view.
Precisely. This holistic scorecard approach ensures you get a comprehensive view and, importantly, forces you to reconcile different data streams. If all streams point in the same direction, for instance, if you're younger by the clock, fitter by functional measures, and have healthier lab results, that provides strong, converging evidence of a true anti-aging effect. If they don't align, it offers invaluable clues for further investigation.
Give us an example.
Okay. For example, if a trial of a new senolytic drug shows no change in epigenetic age but demonstrably improves lung function and lowers blood pressure, you wouldn't dismiss it. It could still be beneficial through those specific improvements. Conversely, if a fancy gene therapy lowering epigenetic age by 5 years, but people don't feel or function any better or they experience side effects, then its true value should be questioned.
That's a wonderfully comprehensive framework, providing a clear path forward in this complex field. We've covered so much ground today.
We have indeed, and it brings us back to that driving question from the intro, the tale of Eleanor and Evelyn. Why does one person age faster than another, and can we change that fate?
The core question.
As we stand on the precipice of this rapidly evolving field, with the promise of better, more reliable, and hopefully more mechanistically informative clocks, and with multi-omic profiles becoming increasingly accessible, the ultimate goal remains clear. By carefully measuring and intervening, armed with both boundless curiosity and a healthy dose of skepticism, we move closer to being able to truly infer causation, not just observing that healthier people have younger biomarkers, but actually causing someone to biologically age slower and seeing them live healthier and longer. That truly is the ultimate goal of this entire endeavor. Until then, we measure, we question, and we learn, always keeping our clocks honest and our minds open.